Hello everyone, let's go ahead and take a look at RiemannSums, which is the foundation of definite integration. Now, what we're going to do in order to go ahead and determine the area under a curve is that we're going to approximate it first by using rectangles. Now, what I have here is a curve that is on the closed interval from 1 to 4. And notice that I've already gone ahead and drawn some rectangles. Now, it's going to be important for us to exactly recognize which rectangle we're using to go ahead and approximate that area. But before we actually go ahead and take a look at that, let's take a look at the area of a rectangle, which is very, very simple. It's just going to be the length times by the width. Now, the important thing for us to go ahead and associate is for the area of the rectangle and the dimensions of the rectangle is that for this particular case here, all the rectangles have a base width of 1. So if I go ahead and take a look at that rectangle, that rectangle, that rectangle, the base width is all going to be 1. Now, how do I go about determining the height? Because if we want to go ahead and determine the area of a rectangle, we need the base times it by the height or the length. And notice that what I'm going to use is I'm actually going to use the values of the function to go ahead and establish what that height would be. So if I was to go ahead and talk about this rectangle right here, then the height of the rectangle would actually be associated with the value of the function when x is equal to 1. Now, if I went over here and I talked about this red rectangle, the part that goes and extends above it in red, then the height of the rectangle would be associated with the y value when x is put into the function f of x, in other words, f of 4. Okay, so what I'm going to do then is I'm going to talk about two things. I'm going to talk about what is called the lower sum, and I'm going to talk about the upper sum. Now, the lower sum, as it sounds, is actually going to be a sum of the areas of the rectangles whose sum is actually going to be less than the exact area of exact area under the curve. Now, if I go ahead and take a look at this, this is all the blue values. So the blue values, if I go ahead and I take a look at the rectangle, it's going to be this rectangle plus this rectangle here plus that rectangle. So if you go ahead and compare the actual area under the curve and the lower sum, you can see that the actual lower sum is going to be less than the exact area under the curve. Now, how do we go about actually determining what that approximate area would be? Again, we just use the formula for the area of a rectangle. And notice that what I'm going to do here is I'm going to say, well, this is going to be the actual value of the functions, or the height of the rectangle, and of course this is going to be the base width. So if I go ahead and take a look at this rectangle here, the first height is 1 times it by 1, so it's 1 times it by 1 plus, and then the height of this rectangle here is going to be 2, and of course the base is going to be 1 plus, and then this height right here is going to be about 2 1/3 times it by 1. Add all of that up and I come up with 5 1/3. Now, I'm going to also go ahead and take a look at the upper sum. Now, the upper sum, of course, is going to be, as it implies, larger than the exact area of the rectangle. And I'm going to use the red rectangles in this case. So notice that this rectangle over here is that rectangle, and that rectangle. So notice that the upper sum, when I go ahead and then take a look at the height of the first rectangle, the height of the first rectangle is actually this value. So it's actually 2. So that's why I have 2 times it by 1 plus, and then it's going to be 2/3 times it by 1 plus, and then the last one over here is going to be when x is equal to 4, and that's going to be about 2.5 times it by 1. That's going to come up with 6 5/6. Now, what we want to do here is that gives us basically an idea of how we are actually going to proceed. But the thing is that we need to go ahead and actually come up with an expression that's going to be able to give us better and better approximations for the lower sum as well as the upper sum. Now, one thing that we're going to do is we're going to involve what are called partitions. And in this particular case, there are 3 partitions. In other words, I've broken up the original closed interval of my domain into 3 equal parts. Now, if I wanted to break that into 3 equal parts, then basically what I would say is I would take this entire length here, which is 3, and then break it into 3 equal parts. And so therefore I would go 4 minus 1 divided by 3, and therefore I'm coming out with a base width of 1. In general, what we're going to say is that if I go ahead and take a look at my partition, which is going to be denoted by delta x of I, that is just going to be exactly the same thing that we just discussed. It's going to take this upper bound minus the lower bound and divide it by how many times we want to subdivide that. And let's go ahead and just say that it's going to be n. In this particular case, of course, it was 3, but we want to go ahead and let it be equal to n because we want to go ahead and, of course, find better and better approximations by increasing the number of n. So what I can do now is I can actually go ahead and talk about this lower sum. Now, let's go ahead and take a look at the particular notation that I'm using. It says L sub 3. So L referring to the lower sum, 3 representing the number of partitions that I'm actually going to be creating on the closed interval. So what I have then is, when I think about what I did here, I have a summation because all I'm doing is I'm adding these areas up. So notice that I'm taking the summation from I is equal to 3 of f of x of I, because this again would be the height of the rectangle, times it by 4 minus 1 divided by 3, because again that's what we said is going to be the partition width. So what I can do then is, if I wanted to generalize for n number of partitions, then I'm just going to take the summation from I is equal to n of f of x of I times by delta x of I. Okay, so it's going to be more or less the same exact thing when we go ahead and we talk about the upper sum using a u instead of an L. Now the thing is though, is that we have to be careful about this x of I, because when we actually took a look, say for example at the lower sum's first value was going to be determined by this value of x being equal to 1, and then the upper sum was actually going to be determined by this first value of x, which was 2. So we need to be a little bit careful about what we associate with this x of I, but we'll go ahead and see exactly how that works in the worked example there. Now the thing that we wanted to do, of course, is we wanted to make sure that we can actually come up with the exact area, not an approximation, but the exact area. And how do we do that? Now it says that if f of x is greater than 0, so in other words it's going to be a positive function, a non-negative function, and continuous on the closed interval a to b, such as this situation here, the exact area, and let's call that capital A, under the curve and above the x-axis must be between the lower sum and the upper sum. And then by the squeeze theorem, if I go ahead and take the limit as n approaches infinity to all 3 parts here, then of course what we know is that it's going to converge to the actual area. Okay, so that's going to be a nice application of the squeeze theorem to go ahead and help us determine that the lower sum and the upper sum will actually go ahead and give us the exact area so long as the number of partitions go to infinity. Now, let's go ahead and take a look at this particular example here. F of x is equal to x squared on 1 to 3. Now, how do we go about actually using this for our purposes right now, the upper sum to actually go ahead and determine the actual area? Now, let's go ahead and take a look at what the graph looks like first. Here's 0 to 3. Let's say, for example, that this value right over here is 1, so we know that that y value is going to be 1. And then, of course, 3 will give us a y value of 9. So we know we're going to have a parabola there. And let's say, for example, we wanted to go ahead and partition this with n partitions. So what I'm going to have then is that my delta x, or the width of every single one of these triangles, is going to be 3 minus 1 divided by n, which is going to be equal to 2n. Now this is going to be absolutely key to make sure that you get this correct, because if you don't get this part correct, then the algebra will all be wrong, and you're going to have a lot of headaches with that. So make sure that this is correct, and also make sure that this is correct as well. This right over here is actually what x sub I is, or these particular values here, okay, all the particular values, but will then go ahead and generate the heights of my rectangles. Because I've already gone ahead and determined what the width is, I need to go ahead and determine what the height is of each one of those rectangles. Now what I'm going to do is I'm going to say x of I is going to be x of 0 plus I times it by delta x. Okay, and we know the delta x already, it's going to be 2 over n. So now, remember what we said is that if we go ahead and start off with the lower sum is actually going to start off from here. It's going to start off from this value over here, and it's going to go across this way. So this is actually the first height that I need to use. Now, since my integral, my summation is actually going to start off from I is equal to 1, what I need to do then is I just need to go ahead and make sure that my x of I is going to be 1 plus I minus 1 times it by 2 over n. And what we need to do is you need to just go ahead and just check to make sure that you are actually coming out with the correct first height, or the correct x value that will provide the first correct height of your rectangle. Now, if I is equal to 1, then that means that I get 1 plus 0 times it by 2 over n, which is just 0. So my first x value, x of I value, is going to be 1. And for my lower sum, it would be true because that would actually be the height of the first rectangle. Now with the upper sum, let's go ahead and see what that looks like. The upper sum actually is going to be this value. This is actually going to be the first value of x that is going to provide us with the height of the first rectangle for the upper sum. So if I go ahead and let I be equal to 1, then what I'm going to come out with is 1 plus 2 over n, which is of course the delta x value, and sure enough that is going to come out to be accurate. So getting this correct and getting these two parts right over here correct are absolutely essential before you actually go ahead and start doing all of this work. If any of these numbers over here are incorrect, then you're going to be doing a lot of work here that is going to fail because of the fact that these two pieces of information are incorrect. So make sure that these two things right here are you're absolutely certain that you're correct before you proceed on. Okay, so let's go ahead and take a look. We're not going to look at the lower sum. We're going to take a look at the upper sum because the upper sum is going to be slightly easier for us to go ahead and calculate, although technically speaking, we should be doing both. Okay, so the upper sum is just going to be the summation from I is equal to 1 to n of f of x of I times by delta x of I. Now, I'm not going to be writing this lower bounds and upper bounds of the summation symbol because that's just going to repeat. So let's just go ahead and just take a look at what x of I is for the upper sum, and x of I is going to be 1 plus I times it by 2 over n. So there's that value of x of I put into the function to come out with the height of my rectangle, times it by the width of the rectangle, which we know is always going to be 2 divided by n. Now after this, it's all algebra. Take this, we need to go ahead and substitute that into the function, and the function we know is f of x is equal to x squared, so that's what that is. Expand that, and now what we're going to do, and one other thing is that notice that I factored out the 2 over n in front of the summation symbol, because of course the summation symbol is only, we only are concerned about the values of I that are in here. So we can go ahead and factor that out. I expanded that to this, and then after that, by our properties of summation, I can go ahead and distribute the summation symbol to each one of these terms here. Now what happens is that I come up with this. I come up with the summation of 1 from n plus 4 over n times it by the summation of I plus 4 over n squared times it by the summation of I squared. Now this is the case where at this particular point we need to go ahead and make sure that we know how to go about expanding this in terms of n. So remember our properties of the sigma notation for the summation of 1, I, and I squared respectively. Okay? And then we can go ahead and substitute these values into here and into here. And then we can go ahead and simplify. So notice that I'm simplifying this to this. This is going to simplify to this. I then go ahead and distribute the 2, and also distribute the 2 over 3n, collect my like terms, and then what I have is I come up with 26 over 3 plus 8 over n plus 4 over 3n squared. Now remember, what we're going to do then, in order for us to calculate the actual area, is that I need to go ahead and take the limit as n approaches infinity of u sub n. Now, what I did then is if I go ahead and take that limit as n approaches infinity, then I'm going to be coming out, of course, with 0 for this term here and 0 for this term here. So I know that the area is going to be 26/3. Now you have to be careful because actually all I found is what the limit of u sub n is. This doesn't necessarily mean that that's actually going to be equal to the area, unless I also go ahead and show that the limit as n approaches infinity of L sub n is also squeezing the actual value of a to this particular value of 26/3. Now, what we want to do here is we just want to go ahead and check to make sure that everything is actually true. We already know how to go about evaluating the definite integral. So if I was to go ahead and integrate that definite integral from 1 to 3 of x squared d of x, of course I come up with 1/3 x to the third, evaluated from 1 to 3, and sure enough that's going to be coming out with 26/3, which is exactly what we're coming out with as the limit as n approaches infinity of u sub n. So notice that this is basically the foundational work of how we actually came out with the connections to the definite integration, which we'll talk about in the next video. Okay, so just to go ahead and wrap up again, Riemann sums, okay, the foundation of definite integration is going to be using rectangles to go ahead and approximate the actual area under a curve on a closed interval. We have what is called the lower sum as well as the upper sum, the partition value, and how to actually, the partition value which is n, and the widths which are noted by the delta x sub I. When we go ahead and apply those, make sure that this particular value is absolutely correct and that these two particular values are absolutely correct as well before proceeding to determine what u sub n is and L sub n is. And then after that, if you can go ahead by using the squeeze theorem, taking the limits as n approaches infinity of all of these parts, you will in fact have determined the actual area under the curve. Okay, so we'll go ahead and take some questions the next time that we meet in class. See you next time. Bye-bye.